think we can start. So good morning, and today I was speaking with Andreas Hohl from University of Leuven, and he's going to talk about the geometry of Fourier transform and systems.
Thanks a lot. And first of all, thank you to the organizers of this conference, in particular Jordan, for inviting me and for organizing this nice event. So today I will speak about the geometry of the Fourier transform of Stokes data. So we have seen a lot of, or we've heard a lot the word Fourier already in this conference. We have heard the word Stokes matrices a lot. So there is a natural question to bring these two things together that I will sketch in a second. And in the end, I will talk about the geometric intuition for this Fourier transform of Stokes data, although you will see that what I will do is probably more topology than geometry, because we're going to talk about fundamental groups. So what is the question I will try to answer? So this conference is about the geometry of ODEs. So if I have a linear ordinary differential equation, I can associate to it Stokes matrices or Stokes data. And of course, I can consider the Fourier transform to get, so if I start with a linear differential equation, I can apply the Fourier transform to get a different ordinary differential equation. And also to this one, I can associate some Stokes data. And so the natural question, if you look at this diagram, is, can I describe directly what happens on this side? So if I give you the Stokes data of some differential equation, can you or can I determine just from this the Stokes data of the Fourier transform without going through the analysis and vector topology? So this is the question. And this is, in general, a very difficult question, which up to now is explicitly understood in special cases, and one of them I will present you today. But in general, it's a very difficult question to answer. And I will tell you more about this. What I will do is there are probably going to be a lot of technical points that I will try to skip a bit and not insist on technical details, but try to give you, even if some of you don't know all the notions that I will use, to give you a feeling for what the main points are, what the main arguments are, and what goes into this construction. So I will redraw this diagram in a more explicit form, so this is more intuitive for now. So let's start by describing what does it mean to have topological data for differential equations. So I will start with a classical equivalence. I already saw this briefly in a talk yesterday, namely the Riemann-Hilbert correspondence, still without Stokes phenomena. So the Riemann-Hilbert correspondence for regular singularities which I will attribute to Levin. So if X is a complex manifold and D is a divisor, then we have the following equivalence. On the one side, we have some analysis, so we have meromorphic connections. If you want meromorphic differential equations up to equivalence on X, which holds FD, and I forgot the word, regular. Yes. So I guess flat is included in the definition of meromorphic connection. Okay. And on the other side, yesterday it was called monotony data. I call it local systems outside the device. So the local systems are basically the same as monotony data, so representations of the fundamental group of X minus t. So let me give a very easy example for this, which you probably is clear to you, but I still give an example. Let's say we are on A1, so on the complex plane. Our singular locus is supposed to be the origin. And I consider the differential equation f prime plus 1 over 2z f equal to 0. This is a meromorphic differential equation. And the solutions, you can guess, the solutions of this are multiples of the function 1 over square root of z. So some complex number c. So of course this expression doesn't make sense globally because the complex square root is not defined globally, but it means locally outside the origin. So this is the space I'm considering. And locally on a thing like this, I have a one-dimensional space of solutions because I can choose a branch of the logarithm, so this makes sense. Globally, I might not have any solutions, but I can describe what happens if I continue this analytically once around the generator of the fundamental group, and this would, in this case, lead to multiplication by -1. So the data associated to this differential equation is the representation of pi1 of the punctured plane given by this generator of the fundamental group, which stands to multiplication by -1. So this is a local system, and Dylan showed that this is an equivalence. So these data determine uniquely up to equivalence pure meromorphic connection. This is only equivalence. We have this assumption of regularity here. Something like the poles that appear here are just poles of order 1, which leads to the fact that the solutions only grow, they don't have essential singularities. They have something like poles or ramified poles. So the question is how to generalize this. What happens if I have irregular singularities, if the solutions involve like essential singularities? So let me give an example that falls outside of this context. Still very simple. I write down a different differential equation that doesn't fit in this regular context, namely this one. You can guess again what the solutions are. The solutions of this are multiples of the function e to the 1 over z. And of course, I can still describe what the local system is. The local system is the one. Well, is the one. This is a globally defined exponential. So the local system, locally, I again have a one-dimensional solution space, and the monogamy here is just the identity multiplied by 1. So this local system exists, but you see that this is somehow the local system of this would be the same as the local system for just the function 1 over z without the exponential. So somehow there is no way just by looking at the local system to distinguish this regular and this irregular thing. So to describe irregular, meromorphic connections, it seems like you need some more data than just the local system of solutions.
So but when you want to solve the Riemann problem, you have to get the behavior of those, describe the behavior of the function which solves the Riemann problem, like some exponential k or something. So basically, in this way, you select.
You mean in the irregular case?
Yeah, you can select which function you want to define.
So I don't know if you understand your question correctly. So you say. So what I want to do now is, okay, I see that this local system is not enough. So I need to talk about something like Stokes phenomenon.
I suspect
Is this what you mean?
I suspect that you see, you are speaking about the Riemann boundary value property. Yes. You want to set a Riemann. His interest is something more, say more. Here is just look at the representation.
Yes, you see if you look at the representation. Yeah, sorry.
So okay, so we see that in the irregular case we need more data. And what is this more data? This more data is basically the Stokes phenomenon that we already saw in some talks this week. And I will recall it now in a way that is adapted to what I want to do. And this means I will recall you what it means to be a Stokes local system. So an extension of just local systems that we saw here. And all this is basically an exposition of, so this notion of Stokes local system is due to Philip Boalch, so about taking into account everything we know about Stokes phenomena. This is a particularly nice way that was developed by Philip to encode these Stokes data. And so what is it? So how does it work? The classification of irregular singularities. So let's say we have, I will work now only on A1 with singularities at the origin. I will take a meromorphic connection there, which might now have irregular singularities. And we saw this yesterday in David's talk, that if I want to talk about irregular singularities, the procedure is always, I have some formal solutions that are particularly nice, and those might be lifted, they have asymptotic developments, they have asymptotic lifts to analytic solutions in certain sectors. And this is what I will do now. So the first theorem is what we usually call the level 2 routine theorem, which basically tells me that there are particularly nice formal solutions to this thing, which means in the formal language means if I take M at 0, so the stalk at 0 if you want, and then formalize it, so I extend it to a module of a formal power series, then formally it is isomorphic to, and I will explain what all this means, to a formal module of this. So the example here is a differential equation. It has a solution e to the 1 over z. In this case, I will denote the associated meromorphic connection as e to the 1 over z, and similarly e to the phi for different phi's. So this is something that has solution e to the phi. And this is something that is a regular. And the phi's, this thing is a finite subset of exponents that have a pole at 0, so it is a finite subset of this thing, the polynomials, the raw polynomials without constant term. And then I need one more thing. You need to pull back via some modification map of this form. So this might look very, very technical now, but what it actually means, so the feeling, the intuition you should have about this is formally there is a basis of solutions of the form, well, an exponential e to the phi times some function r of z, and this is something regular, which means this involves, well, this might involve formal power series, logarithms, and so on, but no exponential, no essential singularities. So this is the idea that the module has formal solutions of this particularly natural form that involve, in particular, these exponentials. So this is the first step. Sorry, yes.
So about that capital phi, you said it is a finite subset of that.
Right, so this is the set of the exponentials that appear here.
How do you select it? I mean, what it depends on?
So it is, it's determined by,
Okay,
so the differential equation determines you the set of exponents that appear in this. So all of this data is determined by m. So there is an, so if you want, there exists this subset, there exists this m, there exists these r phi's that we have decided. I will do some simplifying assumptions here now for the rest of the talk. Namely, I will assume that this ramification is not there. So m is 1. And I will assume that all these exponents are monomials of the same polar order range. Okay? This is not always strictly necessary, but I want to try to start to have some nice symmetries that we wanted to avoid talking about ramification.
Maybe I make a comment.
Yes.
This is exactly the same that the existence of the formal fundamental matrix.
Yes.
Formal fundamental matrix. Exactly. So different way to write the same.
Yeah. So the existence of
the gauge transformation is hidden because in the isomorphism there is hidden the gauge transformation. So part of the nice part of the fundamental matrix, otherwise.
So isomorphism of meromorphic connections means there is some gauge equivalence that transforms this into a nicer form.
What about the uniqueness of this isomorphism?
What do you mean by?
Maybe is it possible that there exists other
I mean, already the fact that this thing has non-trivial automorphisms in general means that there are different, and you can have different isomorphisms.
They are intrinsically defined, but the isomorphism can be. We have various isomorphisms because we can have some automorphisms. Particularly when you have parameter.
So any one of the phi has dimension more than one.
So But what I'm going to do, m equals 1 is not an essential assumption. You will see in the end that we can do without this. We actually have to do without this because this is not preserved on the Fourier transform. This is an essential assumption for what I do. So we only find a solution to this problem in the case where the exponents are of pure level, as we say, so they are monomials that have the same whole order. So this is a formal picture. We have particularly nice formal solutions. The problem is these are in general, as Dr. told us yesterday, not convergent. So they are not actual solutions of the analytic problem. So these U hat are not convergent in general, but, and this is now the good news, on certain sectors, one can, even in a canonical way, lift them to obtain an analytic solution. I go to the formal meromorphic connection language again. So what does this mean? The blue to add something to the blue thing on the right. This means on sectors there exist U which are in a certain sense. So if you know asymptotic analysis, you will know what this means, are asymptotic to the U hats that I found there. So you can approximate these formal solutions in a certain sense by actual solutions. So these are analytic functions. And in the formal language of what does this mean? It means that if I restrict the meromorphic connection to a sector, I don't have the hat here now, so no, this is now no longer formal. Then this is actually analytically equivalent to a system like this, but only on the system. I'm lying a bit when I write this, but put it in quotation marks for those of you who know what's going on here. Actually, what I need to do here, we have to work on the real blow-up space. So I need to pull this back to real blow-up and restrict the sector, but this is a technical thing that I would say is not important to understand the idea here. So on sectors, this formal thing leads to an actual isomorphism, but only on sectors. So different sectors might have different of these isomorphisms that are not compatible by analytic continuation. I was just talking about uncertain sectors. I can make this more precise. So these lifts exist on sectors between, yesterday we saw the Stokes rays in the sort of dark thing. There are also anti-Stokes rays, which are the ones that are basically in this situation in the middle between the Stokes rays. So there are also anti-Stokes rays. If you want, they are defined by those directions where the imaginary part of the difference of two exponents vanishes. So these are also canonically defined as soon if you have m, you have the exponents, and if you have the exponents, you have these anti-Stokes directions. So in your picture, there are certain directions that are called anti-Stokes, and on each of the sectors between these anti-Stokes directions, we have such an isomorphism. We have these analytic lifts of the form of groups. But maybe if you cross one of these, they might not be compatible. So this is basically the Stokes phenomenon. And how do I put this now in a nice picture to get something like a local system? So let me summarize what I did up to now. The upshot is, if I'm given n, it determines a formal model, let me call it n, which was this direct sum. And it is locally on sectors identified with this one. We will add something new. This is why we space. And naturally identified with it. And this is what we found out on sectors. Now, of course, if M is identified with any on sectors, this also means all of these I can associate local systems that I showed you at the beginning. So then also the local system of M is identified with the local system of N. Right? So I just apply the solution function to this equation.
Certainly, there's a question. I'd like to understand what is the difference between a statement like this one and the statement like to have a formal model.
This is the summary of everything I did.
Okay.
Taking all this together, I just reformulated. So tell you again.
Okay.
This is for that. So the question is there an object where I can put all these data together? So so this is again a reformulation of what I had. If I start with a meromorphic connection, and it determines the following. It determines, of course, its local system of solutions. Okay, so a local system on the punctured disk. It also determines the local system of its formal model, which is also a local system on the punctured disk. And if you want, this is the direct sum. So this comes with the decomposition of the local systems of these R phi's that appear. Okay. So it determines a local system of M, a local system of the formal model, plus some identifications between them. Now I want to put them together. So we do some topology again. Well, this is a local system on the punctured plane. I can also consider it, if you want, I can make this circle or this puncture here a bit bigger. So it is the same as a local system on a space like this. I mean, it's just a small deformation. This thing, I can say, well, it's a thing on the punctured disk. I can also say this is the same as a local system on a space like this. And it's also just a small deformation. And now I know, okay, I can also put the punctures here that correspond, I mean, at every, any of these anti-Stokes directions, I take out a point, it still has the same fundamental group, so it doesn't change anything. I do the same here. So these are the anti-Stokes directions. And now I have these identifications which tell me outside the anti-Stokes direction, this local system here is isomorphic to this local system here. And the same for all the others. So actually what I can do is I can take all these data together and glue them to one object that I've got really big picture here. I have the local system, this local system here, and I put this inside and glue it by the formal local and the local system of actual solutions here are glued to one local system on this a bit modified space. So we get a local system on the space that looks like this. So it's a punctured plane minus some more punctures that correspond to the anti-Stokes direction. Okay? And this local system is now called the Stokes local system. Oh. So if these punctures were not there, it's just the usual local system of on a punctured disk. But if I speak about irregular singularities, I have this discrepancy because between the actual solutions and the formal solutions, and putting all this together in one picture gives me a local system on this modified space. Okay? So in the interior here, if I work here, I always think about this is the formal solutions, and outside here, I think this is the actual analytic solutions. And parallel transport along something that crosses from interior to exterior is the identification, the lifts that I have between different formal and analytic solutions. Okay? So this is the picture, and actually,
it's not important to keep track of the curves, meaning you just forget. I mean, you glued something, right?
I glued something, yeah.
And you don't keep any more track.
No, so because so this is a local system outside, this is a local system inside, so there are two sheaves. If I want to glue two sheaves, I need to give an isomorphism on the overlap of the two spaces, and then I get another sheaf. So what I have here is a sheaf up to isomorphism on this space. So also in the local system, I mean, the local system doesn't give you the solution, it just gives you up to isomorphism a sheaf of vector spaces. It tells you how solutions behave.
So it should not fit to the local system of the true solutions, as I say.
It is the space of solutions, but up to isomorphism in the category of vector spaces.
Okay, okay.
No prepared basis.
Right, you can choose different bases and then you cut. So maybe this gets more clear in a second. So of course, what we expect now and what is true is the following generalization of what I wrote down as the Riemann-Hilbert correspondence of Deligne at the beginning. So with this, we have, if I drop the word regular, so now I have any meromorphic connections on A1 with a pole at 0, I can associate to it the Stokes local system. Let's say I also fix the set of exponents, then I get a Stokes local system on this modified surface that I call and okay, x equals A1. Okay, and this is an equivalent. So this is the generalization that was proved after this notion was established by Philip Boalch. This is natural generalization of the equivalence that Deligne gave us. So we don't consider the local system is not enough, but the Stokes local system, which means a local system on a slightly more punctured space, captures all the information that we need about the system. You might wonder, if I look at this picture, I mean, up to now we were always talking about Stokes matrices. When do we see these Stokes matrices in this picture? They should be there. So, what were the Stokes matrices? Well, the Stokes matrices were, okay, on different sectors, I lift the formal solutions maybe in a different way, analytic solution. I compare these two bases. This is the Stokes matrix. And so, if I choose a base point here, let's say I choose a base point here, then a local system is a representation of the fundamental group. So I need a basis of the fundamental group, which consists of one loop around here, one loop around here, one loop around here, one loop around here, and one loop around here. This is the basis of the fundamental group. And for example, between the 1 is 2, S3, S4, the monotomies around these punctures are the Stokes matrices. Because I told you, if we work in the interior, this corresponds to the formal solution. So if I'm here, I start with the formal solution, I move out, I walk out, means I identify this formal solution with its analytic lift in this sector. Then I identify it back with the formal solutions on a different sector. So this loop is actually exactly what happens if I compute the Stokes matrices. So the monodromy around these punctures are what I call the Stokes matrices. And the monodromy around this inner thing, this is the formal monodromy. Because on this inner thing, there lives the direct sum of these R phi's from the regulatory routine decomposition. So this is the formal monodromy, these are the Stokes matrices. So I call this inner thing H and the other S. And if I multiply them all, compose these paths, you will get a path that goes around here. And this is the classical monodromy of the local system of solution. Yeah, it's the monodromy.
And these are X in the Boalch is very real go up we were mentioning before. It's a second one you mentioned.
Right, real blow up basically means that here is a real circle and not just a function.
Yeah.
Yeah, so I can talk about different directions, singular points, not just about the point itself. So this is, I think this is a technical thing. Syntax. Okay, so now I talked a lot about how this Stokes local system works and what they mean. Actually, I want to tell you now about the Fourier transform. So I will quickly do this.
Yeah, just here I cannot see yet why you have to assume that the function phi are monomials. And you can switch
Yeah, so for this, for everything I told you up to now, it's not strictly necessary. But for the Fourier transform that I draw in a second, you will see that we somehow use it because the picture is modified. Okay, so let me. I'll speak about the Fourier transform. So we do Fourier transform at infinity, so we slightly change perspective. Up to now, I told you we're working on the complex plane, the singularities at the origin. Now I will work on the Riemann sphere and the singularity at infinity. So we say we have meromorphic connections on P1. P1 is the Riemann sphere, complex projective space. Singularity at infinity and exponents of some type phi, where phi again has the same assumption as before. Monomials of the same whole order, and you might neglect some of these conditions, but I write them down because this is the case where we explicitly did everything. And the same amplitude, so the coefficient of this monomial always has a fixed absolute value. So this is the thing that I impose on that. And then I get a Stokes local system on this space. So what does this space now look like? We're no longer in the A1, 0 situation, but we have P1, the singularity is at infinity, so the picture will, you need to change perspective, so do some mental yoga, and you will see that the picture, so this surface that we consider now, looks like this. We have the origin in the middle, and then the circle the singularity is this one. So this is very far outside. This is a circle at the singularity, and you have some punctures near this circle. So it is a local, this point is included, not excluded. So this is the origin, this is infinity, and you have these artificial functions. This is just change of perspective from 0 to infinity. And now I redraw the picture in a slightly more correct way. From the beginning, we do Fourier transform, which means we get, again, a meromorphic connection on P1 with a singularity at infinity, and exponents, so the exponents might change, so I call them phi hat, and this again corresponds to Stokes local systems on now this fields. And what does it mean the exponents change? This is something we understand very well. And this is due, let's say, to Lagrange. So how does the formal type, how the exponents change on the Fourier transform? This is given by the so-called Jean transform. What does it mean? So if I have an exponent in phi, then the differential transform is given by the following rules. So this is f is a function in z. So I define a new variable by saying f prime of z, and then g of w is defined by f of z minus z w. So this is a transformation that you can do, and Lagrange shows that if f is an exponent of a system at infinity, then the Fourier transform has the exponent g defined by this rule as an exponent. So this is something well known. And what we want to do is understand what happens. So if I give you a picture like this, a local system on the space, can I just, by some topological stuff, construct a local system on the corresponding space after the Jean transform? So I will do this.
This has no more problem. It's regular 0. Your no connection has no more problem.
So this is, there is no singularity at 0. The only singularity is at infinity, which means on this outer space, this is the formal solutions. On the inner space, it's the analytic solution, but they are actually a constant local system because this inner space is the contractible. So in this case, yeah. You can also think about, of course, how does this work more generally if you also allow regular singularity at the origin and stuff. So this all gets, you can go to more complicated cases, of course, but it's already complicated enough in this case, but that can happen. Sorry, someone gives me a picture like this. So someone gives me maybe even the Stokes matrices. So someone tells me I choose a base point, and your Stokes matrices, I can write them down. From Random Stokes matrices, and then you want to know what happens after Fourier transform. So again, you have a picture that maybe looks a bit different, but you can also ask what are the Stokes matrices in this picture. So this is the original system, and this is your Fourier transform. And how basically the Stokes matrices here, the paths here related to the paths here. And I mean, it would be nice to say something like, well, they are very directly related or even the same. This is in general doesn't really make sense because the choice of this base point is very arbitrary. You can put it wherever you want. So you would need a rule like if I choose a base point here, then on the other side you have to choose the base point on a certain spot. So you would need a relation, but this base point is very non-canonical. So it's not, you cannot expect that there is a very direct relation between these paths and these paths. But the idea is still certain paths, and by path I mean, well, paths where I can power the transport. On both sides correspond to each other. And as I just explained, it's not, you cannot expect it to be as direct as you would maybe like, but there is no work of Takuro Mochizuki, and this is at the basis of what we did. Everything of this, I forgot to say, is joint work with Jean Douçot. So we looked at this big paper of Takuro Mochizuki, which is called Stokes shells and Fourier transforms. And there he basically solves this Stokes Fourier problem in very great generality, but we wanted to make it very explicit in this language to understand really and to make explicit computations. And so let me just think what I showed you in the last 2 minutes. I will draw a picture here just to give you an idea what this algorithm is that we found. So I'm just convincing an example. Actually, the example that I secretly already drew all the time, the example of the pure Gaussian case, which means the exponents are of full order 2. So if we start with a system like this, so let's say we have exponents. Let's say we have exponents 1/2z squared, and this is very explicit. And this one, I told you the coefficients have to have the same amplitude, so this is where there is complicated numbers. That these two, then this means that there is a Stokes local system on a space like this. And I will datum. So I will draw basically the graph of the real part of this exponent, which looks like this. If you draw the graph along in terms of the arguments for very large absolute values of z, it is basically a sine or cosine. Yeah. You will also draw the second exponent, which is the same but a bit shifted because there's a different coefficient. So this one might look like this. So these are the two exponents. And on the other side of the Fourier transform, we have something similar. With 4 of these anti-Stokes directions, and we have the exponents. If you apply the Legendre transform, you find that the first exponent is transformed to this, the second exponent is transformed to this. We can again draw the graphs. We draw again the graphs, which in this case look like this. Now what to do is, so I told you the problem is the choice of base points, which are not canonical. So now we choose canonical base points, a lot of them. So these are the exponents. So we have somehow distinguished, automatically determined sectors where these exponents are positive real part or negative real part. So just for every of these sectors, I choose a base point in the middle. And they will correspond automatically to base points on the other side, because these circles correspond to each other. And I do the same for the other exponent. So here, if I do this, I somehow have a canonical correspondence between base points on both sides. And then well, this is now derived from Mochizuki's work. I have some paths that correspond to each other. For example, if I walk from this red point to this red point, there is a path that connects the two. The parallel transport along this path is the same as the parallel transport along the path, the corresponding path on the other side. And then there are some more distinguished paths, for example, the parallel transport along this path here will be the same as the parallel transport along the corresponding path on the other side. So the work of Mochizuki tells you exactly, if you reinterpret it in this language, that there is a certain number of paths that you can connect between both sides. And so there are paths. So just a second. That you can identify on both sides. And this determines, so this collection of paths, I haven't drawn all of them, this determines the local system and hence all the Stokes data. So if well, with a bit more time, I could show you that this really leads to an algorithm where you can explicitly compute the Stokes matrices on this side if you are given them on this side. But maybe you already got some intuition about what happens.
Sorry, a question. I'm trying to understand the logic of when you say, so you have a path there, like in white one path, and then you say the corresponding path, or vice versa, I don't remember which should go first. But again, can you repeat the corresponding? What is the I mean, because there I don't see, I have two nodes, a yellow node and a red node, and in between somehow no other dot. Whereas there I have a yellow node, red node, and then in the middle, I'm trying to understand.
You mean just like dots?
No. In this.
Yes.
So the question is, what do you mean by corresponding?
Yes.
Okay, yeah.
Yes.
So now okay. I mean, there are more details. There's a lot of things I didn't say, of course. But so I told you I choose a base point. I choose 4 base points on the red circle here. And they correspond by the Legendre transform. If you go through the formulas, they correspond 1 to 1. So the Legendre transform basically gives you a bijection between this red circle and this red circle. So each of these points, so for example, this point corresponds to this point via the bijection.
Okay.
So if I have a path here, it starts at this, it ends at this, and these points have 1-to-1 correspondence on the other side. So I can also connect them.
Can you make a correspondence between the endpoints of the path and then from the endpoints? You just can define the path to start from the endpoint. You go to the interior.
You go inside and you walk out.
And you just put some labels.
The question is why, how do you correspond to paths? I mean, paths could be very.
Yes, that's right. So there are rules to make this explicit. So the rule is you start at this point, you walk straight into the middle of the surface. So you walk from the formal part to the interior, just as given by the angle where you are. And then you walk straight out at the end point. So there is something to do now. But what I wanted to do is give you a feeling that there are these paths that correspond 1-to-1. So if you know all the monodromy data on this side, you will know enough monodromy data on this side to determine everything.
Nice. Okay. So everything is given by an algorithm. So you don't have a formula. You have an algorithm.
The explicit formula will depend on some choice of base.
Right. If you want explicit formulas, then, if you really want to work with explicit matrices, you need to choose not just the base point, but also a basis at these base points. And of course, then nothing is unique anymore because you have like two conjugation or up to whatever you can.
In the case there, where in the very simple case where the coefficients are all positive multiples of the same one, then you have an explicit formula. But whenever they start moving, the picture behave much more.
Yeah, one simple tip, like if you try to choose like a kind of more canonical base point, for example, attached to the real circle, and then yeah, it will move like according to the Lagrange transform, but like if you chose canonical base points like associated to the yellow circle, they will move in different way. The yellow circle, like the red circle, they cannot move in opposite direction when we do the Fourier transform. So yeah, there is no perfectly canonical way to choose the base point.
So let me say where this case comes from. So this was, I did with different methods. I considered this in my PhD thesis, for example, following a work with, again, different methods. Claude did already in 2016. So this pure Gaussian case, always with a bit different method, with a bit different like assumptions on the exponents, has been considered and relatively well understood already in works before that. I would say this covers some more spaces, cases that we haven't seen before. Especially if so in the work of Claude and also my work, we always had the thing like the exponents must be close to each other. So the polynomials that we have are close to each other in a certain sense. This is not necessary for this algorithm anymore.
Okay, so I propose to postpone other questions to the coffee break, and let's have the speaker